Wait one moment. I think I hear somebody coming. No. So I'm very pleased to introduce Tim Roughgarden from Columbia, who will tell us beyond worst case.
All right.
I hope that sort of says better than worst case and not worse than
exactly. There's some parsing ambiguity. I definitely mean parentheses beyond worst case analysis. Exactly. Thanks very much for coming, everybody. I was talking with Ari beforehand. I think this is something like 5 or 6 at IAS over the course of my career. It's always very memorable whenever I come back because the first visit, I'm pretty sure it's 23 years ago, fall 2002. Avi, he didn't know who I was. He was already famous, obviously, and he just sort of thought I was doing some cool work and invited me to come give, what was the Monday morning seminar. Had a great visit. In addition to all the stuff happening in the math department, he invited me to what was going on in the economics department. So Eric Maskin was here at that time. And Ilya Segal was visiting. Those were some of my earliest conversations about my work with kind of sort of really serious economists. Meanwhile, Arit, believe it or not, I was office mates with, I think, 22 years ago. So very cool to sort of see her now. So it's sort of great to be back. So a little bit about me. So my original training is in algorithms. That's also what I'm going to be talking about today. A lot of my career, I've actually worked on the boundary of computer science and economics. So I'll be giving a public talk on Wednesday, which is much more sort of focused on that part of my work. So you won't see any economics or game theory per se today, but there's still sort of a funny story there, which is, I mentioned how in that 2002 trip, talking to some economists here, and it's amazing how when you describe your work to people from different communities, they just ask really different questions sometimes, right? So I was used to, I was trained as sort of a theorist. So the question usually for me would always be is there a matching lower bound, right? And then I started talking to some economists and talking about my work. And they started asking me questions like, how should I interpret this result? And I was like, at first it's kind of like, what are you talking about? There's the theorem, there's the proof. Do you have any questions? But I'm planning to see. And I started thinking about it because it's really easy. So I think in complexity theory and that part of theoretical computer science, I think this is very strong tradition of very strong conceptual content and interpretations. Look at the P versus NP question or something like that. I think, the conceptual meaning of that sort of jumps out at you. In algorithms, it can be sort of chasing better bounds. And so that really got me thinking. And in some sense, this area beyond worst case analysis that I've worked a bunch in came, sort of was one of the sort of fruit that blossomed from those seeds with those conversations with economists. Okay, so let me just start really high level. I'll get more technical as we go along, but just sort of by way of introduction, there's sort of there's an odd asymmetry if you teach sort of undergraduate algorithms like I have many times, between the way you talk about algorithm design and the way you teach algorithm analysis. So when you talk about algorithm design, something that's kind of obvious to everybody is there's not going to be one silver bullet algorithm. The algorithm you're going to use to solve a problem, it's going to matter whether you're just sorting numbers or whether you're solving a linear program. Right? You're just not going to use the same kind of algorithm for those two different tasks. So if you look at a typical algorithms class, the curriculum is broken down into categories. And within a category, you talk about a family of algorithms, which aren't useful for all problems, but they're useful for a decent chunk of the problems you might encounter. So you'll talk about greedy algorithms for a week or two. You'll talk about dynamic programming. You'll talk about optimization, and so on. And in addition to teaching that toolbox, our job as sort of teachers is to also say when is which tool going to be applicable. So what are features of a given problem that might suggest you use one of these tools rather than another? But when we analyze algorithms, again, in a traditional algorithms course, we act as if there is some silver bullet way of analyzing algorithms. There's a one size fits all of understanding what makes an algorithm good or not. And, with rare exceptions, all that you do in traditional courses is worst case analysis, which means you make no assumptions about the input being fed to the algorithm. It could be literally anything. And you want to prove some theorem that says the algorithm performs well, say runs quickly, no matter what that input is. Again, that's pretty much all you focus on in sort of algorithms as it's sort of taught to undergraduates and graduate students. Researchers in algorithms, we all know that actually there's plenty of famous cases where worst case analysis is just a disastrous model to use. Lots of examples. Maybe the most famous one, Danzig's simplex method for linear programming. Empirically, terrific performance, 80 years in, still going great. About a little over 50 years ago, Clay and Minty came up with their Clay-Minty cubes. So these very contrived linear programs, which actually force the simplex method with any of the common pivot rules to run in an exponential number of steps, exponential in the dimension. In practice, it is literally like impossible to find a linear program that exhibits this exponential running time behavior. But if you use worst case analysis and you sort of optimize for it, you will discover Clay-Minty cubes. Okay, maybe a more modern example would be sort of in modern machine learning, where a lot of the machine learning training that's been done both this decade and last decade, sort of in deep learning, those are non-convex problems that theory would tell you is unsolvable. And yet even using very simple algorithms like gradient descent, in practice, people do get sort of very good algorithm performance for those non-convex problems. Okay. So what goes wrong? I mean, the first obvious thing is just that worst case analysis is overly pessimistic. Okay, it just focuses its recommendation just on one single input, ignoring the rest of the input landscape. I could maybe live with this if at least qualitatively it gave you good advice. Okay, if at least what it singled out as the algorithm with the best worst case performance actually was sort of the algorithm you'd probably want to use for the problem anyways. Okay? But that's not always true. Linear programming, again, here would be a counterexample. There are algorithms that are guaranteed to run in polynomial time, the ellipsoid method being the first one back from 1979. They're much slower in practice than the simplex method, again, on pretty much any input you're ever going to see. So if you take worst case analysis at face value as a recommendation of how to solve a problem, it simply gives you bad advice in the case of linear programming, okay? And the weakness of worst case analysis is sort of the same as its strength, but its Achilles heel is that it refuses to make any assumptions about what the inputs might look like. Okay, so the idea is you're designing an algorithm and you kind of say, look, I'm going to put this out into the world. I don't know who's going to use it. I don't know what they're going to use it for. I have no idea what the inputs look like. I want it to work well no matter what, which is great if you can get it. But at the same time, if the reason an algorithm performs well is because of some kinds of properties about the inputs that arise in the real world, it gives you no model, no vocabulary for articulating that structure. If there's a data model behind worst case analysis, I would call it the Murphy's Law data model. Murphy's Law being anything that can go wrong will go wrong. Worst case analysis is mathematically equivalent to reasoning about your algorithm as if the only input it will ever be asked to solve is one chosen by an adversary as a function of your choice of algorithm. Right? Maybe in cryptography, you actually want to have that kind of paranoid mindset, but outside of that, that's usually just not a very coherent way to think about the world and algorithms. Okay. So what would it mean to go beyond this? Well, basically, as an analyst, you have to work up the courage to write down something about relevant inputs or real world inputs. You need to have some sort of more specific model, okay? And just like with the design of algorithms, there's not going to be one model of algorithm analysis that's always the most appropriate one. This is sometimes going to be problem dependent or even algorithm dependent, and that's part of the job of doing research in this area, okay? So worst case analysis, it's been around for a long time. I mean, back in the 1970s, people like Dick Karp were certainly working on this a lot. But it's really gathered a lot of momentum, I'd say, over the last decade. So I edited a book on the topic a few years ago. It's a sprawling topic. So there's lots of chapters. There's 40 authors, something like that. But all of this is different approaches. It's really an analysis toolbox, different ways of having more nuanced understanding of algorithm performance, along with, again, just like with algorithm design, sort of teachings around what features of a problem or algorithm suggest that one part of this analysis toolbox would be more appropriate than another, okay? There's lots of topics here. Today, I want to do a case study in something known as smooth analysis. So let me tell you a little bit more about that, okay? So a lot of the approaches, not all, but a lot of the approaches to beyond worst case analysis involve something known as semi-random models, which interpolate between, on the one hand, worst case analysis, and the other hand, average case analysis with respect to some fixed distribution. And in a semi-random model, a nature or randomness collaborates with an adversary, and jointly they produce an input, which is then going to be fed into an algorithm, okay? So smooth analysis is one specific type of semi-random model, collaboration between nature and an adversary. This one was invented by Spielman and Tang almost 25 years ago, explicitly with the goal of having more satisfying mathematical analyses of the performance of the simplex method. And the way they set it up is they said, look, adversary gets to pick any linear program they want, like one of those claimant cubes I mentioned earlier. But then it's going to be subjected by nature, it's going to be subjected to a small random perturbation. The specific model they looked at was adding a sort of small Gaussian to each of the entries in the constraint matrix. And then that perturbed instance is the one that gets fit into the algorithm, in this case, the simplex method. And then the goal is to hopefully prove that the expected running time of the algorithm, like the simplex method, is small. Okay? Expectation with respect to the nature's random perturbation, no matter what the initial input chosen by the adversary. Okay? So that's the original origin of smooth analysis. These days, we often talk about it a little bit differently, but it's basically equivalent. Whereas we again think about an adversary coming up with the input, but rather than just coming up with one nefarious input, we force the adversary to commit to an input distribution, which has some kind of anti-concentration assumption about. The adversary is prevented from just picking a single worst case input. They have to at least randomize over some small set of different inputs. And again, you would like to prove the expected performance of an algorithm is good, where the expectation is over the distribution chosen by the adversary. Okay? All right. So this is an approach to algorithm analysis different than worst case analysis. But there's a bunch of different things you could do. So again, it's our responsibility to kind of say like what types of problems and algorithms suggest this approach to algorithm analysis. So let me give you two things where when you see them, it should sort of, a light bulb should go off in your head saying like, this might be a great place for smooth analysis. Okay. So the first thing is that the inputs that are hard, the inputs for which an algorithm performs poorly, should be intuitively brittle, to the point that like you could imagine a small random perturbation may actually completely flip the instance from being hard for the algorithm to easy for the algorithm. And honestly, this you often know it when you see it, and we'll see an example later in the talk will become obvious what I mean by brittle. Also, if you've ever seen sort of the description of like the claimant cubes of those linear programs, it feels again like a super edge case. It feels like if you change the numbers a little bit, maybe the whole thing would collapse. Okay, so that's the first thing. Smooth analysis is especially appropriate when bad inputs exist, some kind of like almost like a measure zero subset of the instance space. The other comment, and this is true for semi-random models more generally, is that any semi-random model is going to be wedged between what you can prove about an algorithm in the average case and what you can prove in the worst case. Okay, this is going to be some kind of interpolation between the two. So, for the question to even be interesting in the first place, you want to look at problems and algorithms where there's a big gap between these two endpoints. Okay, where it's just things are much better average case than worst case. If those are almost the same, then there's not much to say about what's in between. Furthermore, for problems and algorithms where there is a big gap here, it's now clear what it is you're aspiring to prove. You're aspiring to prove that even in the smooth analysis world, an algorithm runs almost as well, like almost as quickly as it would in just the easier average case world. Okay, so that's what a positive result looks like in smooth analysis. It says even though you have this adversary who can pick whatever they want as long as there's sufficient anti-concentration, even though you have this adversary, actually you can still get algorithms to perform as well as you could as if there was no adversary at all, as if inputs were just like IID from some distribution. Okay, so that's at a high level, the idea of smooth analysis. Let me now sort of drill down a little bit further and talk about how this gets applied to specific problems. I'll give you the two main ways it's been applied in the past. Then I'll give you the third new way that's going to be applied in the work I'm talking about today. Let's see, this looks actually slightly out of date. That's weird. Okay, so the first killer application, probably still the most well-known one, is the original one of Simplex and Tang, Spielman and Tang, about analyzing the simplex method. So they proved polynomial bounds. It was the same model I mentioned earlier, small Gaussian perturbations to each of the entries of the constraint matrix. Spielman and Tang established polynomial expected running time bounds in that case. There's been a sequence of papers improving it, and there's actually just one appearing in Fox in about a month by Bach and Hubert, who actually nailed down the dependence of the running time on the size of the perturbation. That's actually a major result. This was just proved this year. Okay. Equally important, in my view, slightly less well known, but equally important, is the running time of local search algorithms. Okay, so a local search algorithm, that's something used for an optimization problem. So you have a notion of feasible solutions, and you have a notion of neighboring solutions, right? So like, I don't know, if you're in a graph, you might sort of take out one edge and put in a different edge. Okay, that would be an example of a local move, like so, say for the traveling salesman problem. And local search algorithms, they're not exact optimization algorithms. They can find suboptimal local optima. What this is about the running time of local search algorithms. So how quickly do they get to some local optima? Okay. And there's a lot of analogs with the simplex method here. Local search in practice always find something quickly. They may find something bad. They might find a bad local optimum. That does happen in practice. But they're going to find a local optimum with a very small number of iterations. But if you work really hard, you can, for most local search algorithms, construct contrived examples that force local search to actually take an exponential in the input size number of iterations before they find any local optimum. Okay, but again, if you saw those examples, you would say those look very brittle. And indeed, smooth analysis has been very effectively applied, showing that local search algorithms, if there's a small perturbation applied to an input, all of a sudden local search runs provably very quickly. Okay. And the two things to know about these sort of big categories of smooth analysis that have been studied so far is they're both about the same measure of algorithm performance, which is that of running time. Okay. So before the work I'm going to describe, almost all work on smooth analysis was specifically about the running time of algorithms. And there's a bunch of other metrics we care about to measure algorithm performance, and we're going to see a different one today. So I'm going to show you a case study of smooth analysis specifically in sequential prediction or online learning, where we're not going to care about the running time. We're going to care about, in some sense, the prediction accuracy of the algorithm, something known as regret minimization. Okay. So now I'm going to dive into this, and this will actually give you a specific model, specific algorithm, specific results.
I'm curious, did the introduction of smooth analysis change in any way how people use the simplex algorithm in practice?
Yeah, that's a good question. So there's a couple of things you might want when you do algorithm analysis, right? So sometimes, you take an algorithm for a computational problem almost as like a natural phenomenon in the world. Like you just sort of take it as ground truth that simplex is fast, and you're just trying to find the satisfyingly convincing theory of that fact. Other times you're really hoping, other times you like genuinely don't know how to solve the problem in practice. And you're hoping the theory will give you guidance to figuring out some new algorithm you haven't seen before. There are plenty of examples of that in beyond worst case analysis, but I don't think we've seen any concrete examples in the talk today. So today's talk is really more about, as theoreticians, how do we explain the empirical behavior that we see of these algorithms? Good question. Other questions before I sort of dive into the specific model here? It's not going to get that technical, but it'll get a little more technical, starting with the next slide.
What's the result about max cut?
Max cut. So here, so what is the local move? So you have to think about local search, right? So max cut, so you have a graph, you want the maximum number of edges crossing between the two partitions. Local moves are moving a vertex from one side to the other. So an improving local move increases the number of edges that are crossing. And so, for example, and then there's some internal, and so you want as many edges crossing as possible. And so, just because there's only a finite sort of number of graphs, every improving move increases the number of crossing edges. It's going to stop. It's going to stop at a local optimum, a local maximum. It may or may not be a global maximum. It's an NP-hard problem, max cut. So you will, in some cases, stop at a local maximum. It is known that in the worst case, you'll get at least half of the maximum possible edges crossing between the two parts. And the theory here is not talking about how many edges you will or won't get. It just says how many times do you have to move things back and forth before you stop at a local optimum.
It'd be local. It will be local. It might
It will not necessarily be global. So this theory does not speak at all to whether the local optimum found is global. And indeed, like in practice, they're often not global.
Yeah.
So any theorem which says with high probability it's going to be global, I'd sort of be very skeptical of the model.
Right.
So Mihalis Yannakakis, my colleague at Columbia, has these very elaborate examples that show that, in fact, you need weights. So it wouldn't be in the unweighted case. It'd be with weights on the edges. In the weighted case, local search may actually move vertices back and forth an exponential number of times before it finds a local optimal solution. And the theorems here say, well, but if you subject the edges to a small random perturbation, then an expectation over the perturbation, local search will find a local optimum in expected polynomial time. And all of these local search results have that same. Other questions? All right. So let me sort of talk about this new application, smooth analysis. So this is going to be a fundamental problem in learning theory, a sequential binary prediction. Really old problem, certainly studied as early as the 50s in statistics by Blackwell and in game theory by Hanan. But now, with machine learning taking off the way it has, I would say every year there's probably dozens or maybe even hundreds of papers written about this model and close variants of it, because it's sort of very, very well studied. So we're going to be looking for an algorithm that makes predictions. Okay, so we're going to feed it something from an input space, X. If you want, just think of this as kind of like the hypercube Euclidean space or something like that. Maybe it represents an image or who knows. And then there's going to be a sequence of inputs that are going to be fed to an algorithm, and we're going to ask it to make a prediction, okay, about, I don't know, whether the image has some property or not, for example. Okay. So at each time step, because it's going to make predictions continuously, and it's allowed to learn continuously along the way as well. So at each time step, the learning algorithm is presented with an instance from the domain. And then it has to make a prediction. And again, we're only going to talk about binary prediction in the talk, so just plus minus one, whether the, for example, image has the property or not. And then following the prediction, the algorithm learns whether it was correct or not. It is told the true label, the correct label, y sub t. Okay. So this is the setup in sequential binary prediction. And, informally, obviously, we want our algorithm to make as few mistakes as possible. Okay, we would like zt and yt to agree ideally almost all the time. Now, that's obviously not a sort of well-posed problem yet, for a couple of reasons, actually. So 2 questions. So one is like, okay, so 0 mistakes would be great. But say you run for 1,000 steps and you make 100 mistakes. Like, is that good or bad? Like, you need some way of talking about that. Like, what's our benchmark? And then the second thing, something that presumably should be in our model somewhere, is presumably some concepts are just harder to learn than others, right? So learning whether or not an image contains, some, human being, like a person in it, maybe that's easier. Whether you want to understand if an image has a specific person, that might be a harder learning problem. And so we might expect to have stronger positive results for your learning problems, which means we need some way to quantify the complexity of the learning task. So I'll answer both of those 2 questions with the same answer. So in addition to the model I just showed you, an important concept for us is going to be a hypothesis class, which is just a set of functions, binary functions, on the domain X. Okay. So the hypothesis class could be anything. If you want to keep a concrete example in mind, half spaces, probably the most canonical example in learning theory, at least. So this would be in 2 dimensions, right? So affine threshold function alternatively. So here's your line. Everything on one side is +1s. Everything on the other side is -1s. That would be an example of hypothesis class to keep in mind. And basically, richer classes of hypotheses is going to correspond to more difficult learning problems. Okay. And sort of smaller classes H are going to be easier learning problems. In particular, for the benchmark, how do we know if 100 mistakes is high or low? For the benchmark, we're going to use the number of errors made by the best hypothesis in hindsight. Okay. So that Process runs for 1,000 steps. There was X1 through X1,000. There were the correct labels Y1 through Y1,000. And we ask, of all the hypotheses in capital H, which one made the fewest mistakes? And that's going to be our benchmark. For example, if all of the XT-YT pairs were in fact consistent with a single hypothesis, the benchmark would be 0. Okay? In general, maybe there's sort of noise in the data, right? So maybe like any of the hypotheses would have 5% error, something like that, in which case we're going to want to ourselves have close to 5% error. Okay? So the regret, okay, and this is again, maybe the most basic notion in sort of sequential learning and online learning, this is the number of errors our algorithm makes in excess of the benchmark. Okay? So if we go for 1,000 steps and the best hypothesis in hindsight made 90 mistakes and we only made 100 mistakes, we view that as pretty good. If the best hypothesis in hindsight made 0 mistakes, then maybe 100 mistakes was not so good. Okay? And obviously, the bigger this hypothesis class H, the more demanding it is to compete with this benchmark. The smaller this benchmark is going to be. Okay? So instead of the running time of an algorithm, we will be looking at the regret suffered by online learning algorithms, because this is a really key metric for this topic. So any questions about this? We're going to try to get this to be close to 0. Okay. All right. And so specifically, right, so in general, regret may accumulate over time, but we want it to accumulate sublinearly in capital T. Okay, so for example, if the benchmark is 0, if actually all the points are consistent with some hypothesis, that this means we want to basically start making mistakes almost never once T grows sufficiently large. If there's some background kind of noise, this is going to say if T grows large, we ourselves will only be making errors roughly 1% of the time. Okay, so I want to study the achievability of this goal. Right, it's going to depend on 2 things. First of all, as expected, on the complexity of the learning task, meaning the complexity of the hypothesis class H. What does that mean? Start talking about on the next slide. Secondly, it's going to depend on sort of the adversary model, by which I mean the process by which the XT-YT pairs are generated. So a very easy case would be if the XT-YT pairs are generated IID from some fixed distribution. That would be like an easy case. A hard case would be we have actually a worst case adversary that knows about our algorithm and chooses the XT-YT pairs specifically to screw up our algorithm. Okay, so the adversary model in that sense will also be important for when this guarantee is achievable. Okay, so what I want to do next is just do a kind of a trivial example. One, just to kind of give you more of a sense of these concepts, but actually this is going to also segue directly into the notion of VC dimension, which is very central in learning theory and also important in this talk. Okay, so here's a trivial example. You got a finite set of points, D, and suppose H is literally just all functions, all binary functions, all 2 to the D functions on capital S. Okay? So intuitively, like learning, non-trivial learning is impossible in this example. You literally cannot interpolate or extrapolate anything from a data point you have seen to one that you haven't seen, right? Because the function you're trying to learn could literally be anything. Okay? So if we translate that intuition to our goal of having low expected regret, okay, sort of making few mistakes, what this translates to is a lower bound of square root dt on the best possible expected regret of any algorithm. Okay, so on the one hand, if d is finite, right, this is indeed kind of sublinear in capital T. So if d was small, we'd be happy with this. But the problem is this is not a bound that's sort of independent of the size of the domain. Okay, so if you have large domains, this basically could mean realistically, you're making a mistake with every single prediction. Okay? So that's kind of the first trivial example. If you have no structure on the functions you're trying to learn, really there's nothing you can do other than sort of memorize the examples you've seen already. You cannot extrapolate in any meaningful way. Easy extension. Now suppose X is arbitrary, X is, again, back to the unit hypercube or something, and you have some hypothesis class, which is not all functions, all binary functions, but suppose there's a finite subset of the domain, say D points, or on that finite subset, the hypothesis class induces all possible binary functions, all 2 to the d possible binary functions on capital S, right? Well, then the exact same argument applies, okay? So previously, all the adversary had to do was generate IID points from capital X. Now the adversary is just going to generate IID points from the subset. But again, right, you cannot meaningfully extrapolate any information you glean on points from the subset to other points. Okay, so you really have to memorize whatever the function is on this particular subset S of points. And so that means you will again be suffering this root times dt lower bound on the best possible expected regret. Again, if d is small, we'd be happy with this. But if d is sort of big or even unbounded, then of course we would not be happy with this. Okay. Another way to sort of think about when you see sort of bounds like this, another way to think about this is it's only once capital T is as big as D or a little bit bigger than D that you start having non-trivial learning. Okay, so you have no non-trivial learning for basically the first D time steps. Okay, so if D is large, that means you really don't learn until you've kind of almost seen the whole function on capital S. Okay. All right, and I want you to notice that this lower bound holds already for the most benign type of adversary model. This holds already if the xt, yt pairs are generated IID from a fixed distribution. Okay, so even with the most benign adversary, if you have subsets with this property, you're in trouble. Okay, and there's well-known terminology for what's on this slide. So when this happens, we say that H, the hypothesis class, shatters S, the finite subset of the domain. Okay, so to shatter a set means you induce all possible binary functions on that finite set. And that we say the VC dimension would be at least D in this case, because it shatters a subset of size D. So again, just to summarize, the VC dimension of a hypothesis class is the size of the largest finite subset shattered by H, the largest finite subset on which H induces all possible binary functions. If you shatter arbitrarily large finite subsets, then we say the VC dimension is infinite. And what we just saw is that you cannot have a regret bound better than root VC dimension times T. Okay, even for the most benign type of adversary that literally just generates all of the inputs from a known distribution, IID. Okay. So basically, meaningful learning does not happen until the time horizon exceeds the VC dimension. Okay? At best. This is saying at best, maybe you have learning at that point. What's not so obvious, but we've known for a long time, basically from the 1970s, is that this obstruction to learning, right, shattered sets, we've seen that's an obstruction to fast learning. That is the only obstruction to fast learning. Okay? It turns out. So we've known for now like a half century that if you have this type of benign adversary, the XT's generated IID from a distribution, then in fact there is a matching upper bound. Then in fact you can start learning as soon as capital T starts exceeding the VC dimension. Okay, so if your hypothesis class has small VC dimension and you have this benign adversary, we're happy with the results. Okay, you get learning pretty quickly online. Okay, square root D times T regret. Okay. All right. So I said, okay, if you have a benign adversary and the VC dimension is low. Okay, but is the VC dimension ever low? That'd be kind of a problem, right? If we didn't have any good examples of interesting hypothesis sets with low VC dimension. But, one reason it's a famous concept is there are lots of examples. Many of the hypothesis classes that we care about in machine learning theory do in fact have bounded VC dimension. Half spaces, for example, VC dimension is basically the dimension of the ambient space, or n+1. If you prefer to have polynomial threshold functions, okay, then it's again going to be bounded. It's going to be exponential in the degree of the polynomial, but it's going to be like n to the k. If you have k-variate polynomials in Rn. And one thing that actually I think only kind of became clear in some work I did with a former student, Rishi Gupta, is that not only natural hypothesis classes that arise algebraically have bounded VC dimension, but natural classes that arise for algorithmic reasons also have bounded VC dimension, or very similar concepts. So specifically, we looked at hypothesis classes that arise from the performance profiles, like say running time profiles of natural classes of algorithms, And those also have what are known as bounded pseudo-dimension, a pseudo-dimension being a real valued extension, sort of analog of VC dimension. And so this actually provided the foundations for a different sort of part of beyond worst case analysis, which is now known as data-driven algorithm design, and is now kind of a really sort of nice literature in its own right. I'm not going to have time today in the talk to speak more about this, but happy to talk one-on-one about it afterwards if you like. The takeaway from the slide is just that the VC dimension of hypotheses classes for the classes we care about is often reasonably low. Okay? That's the takeaway. So that's great. Lots of hypotheses classes have low VC dimension. If you have low VC dimension and you have a benign, meaning IID adversary, you have fast learning. Okay. So the next question I want to ask is, well, that was with an IID adversary. The world is often not IID, right? And, right, but now as the analyst, you have this problem again. It's like, okay, I don't really believe the IID hypothesis, but like, do I need to actually write down some proposal for the way in which the world is not IID? Because that also seems like a potentially thorny issue to do. So you start by saying, wouldn't it be nice if I didn't have to make any assumptions at all about the way in which the world is non-IID? And mathematically, what that means is that let's just go ahead and allow the XTYTs to be chosen by an adversary. Okay, that's the absolute no assumption worst case analysis approach. Okay? Moreover, and this is actually really important for some of the technical challenges that come up, we want to think about adversaries that are adaptive, meaning that the adversary knows not only the algorithm, but at a given time t, they know everything that has happened up to time t. So they know the inputs that they themselves suggested, x1 through xt minus 1, and the labels y1 through yt minus 1 that they themselves suggested, and they know the predictions of the algorithm that it's made in the first t minus 1 time steps. Okay? So this is the next question I want to ask. Could it be the case that still bounded VC dimension is a sufficient condition for fast learning if the data points are generated not IID, but adversarially? Could VC dimension still be a sufficient condition for fast learning with this more powerful adversary? Okay. And so the answer is going to turn out to be no, and that's what I'm going to show you in an example next. Any questions before I do the example? It's a very simple example. Okay, so the answer is no. Bounded VC dimension is definitely not sufficient for fast learning with an adversary. Let's just think about the unit interval. Let's just think about threshold functions of this form. All right. So basically, we know what this looks like. We know there's plus ones here and minus ones here, and we just don't know exactly where the boundary point is between the minus ones and the plus ones. Okay, that's the only thing we don't know. VC dimension of this class is 1. Okay. But with an adversary, you can probably already imagine what's going to go wrong here, right? So the adversary says, hey, what do you think 1/2 is? Think 1/2 is plus 1 or minus 1? Like, I don't know. So you make a guess, maybe it's plus 1. Okay, so that means you're guessing the threshold is over here to the left. And then the adversary says, no, it's minus 1. The adversary is, the threshold is to the right of 1/2. Now the adversary says, what about 3/4? What do you think about 3/4? Plus 1, minus 1? And you're like, I don't know. Maybe I'll guess actually then the threshold is even to the right of 3/4 in that case. The adversary says, no, it's not. It's actually between 1/2 and 3/4. Asks about 5/8. Again, maybe the algorithm sort of guesses that it's to the left of 5/8, but in fact it's to the right, and so on. Okay, and obviously you can continue forever. So H here has VC dimension 1. Yet, worst case adversary can force any learning algorithm, any deterministic learning algorithm to make a mistake every time step. Any randomized algorithm to make a mistake with probability at least 1/2. Okay. And just each data point, so there's this sort of narrowing window of uncertainty, right? So the algorithm knows the correct labels on more and more of the unit interval. There's always this ever shrinking interval where it doesn't know. That's what the adversary is always asking about. So that, of course, is requiring the adversary to be more and more precise with how it specifies the input as this process goes on. Okay. And when you see that, that all of a sudden starts being one of the two signals, you know, that light bulb should go off. You might want to start thinking about smooth analysis. But sanity check number one for smooth analysis. Okay, there are going to be bad inputs in the worst case, but they seem very brittle under random perturbations. Okay. And indeed, if you imagine that, you know, the adversary kind of had a little bit of a shaky hand when they were sort of picking points on this unit interval, right? They might tremble in a way that their input would go to one side of the interval of uncertainty where the algorithm actually knows the answer, right? -1 to the left of the window of uncertainty, +1 to the right. So that's the first sign that maybe this is a good application of smooth analysis. The second sign, the second sanity check, is there should be a big gap between the average case and the worst case. Okay. And we've already seen that that is in fact true. Let me just sort of spell that out a little more formally. I, the adversary, right, we talked through this, right? So there it's governed by the VC dimension. Okay, so D times T, square root, that's the expected regret that you can get. By the way, the tilde notation is suppressing log factors. Seen that before. So that's good, and it's also good that most hypothesis classes of interest have bounded VC dimension. For the worst case adversary, the general result, which generalizes the 1D thresholds case we just saw, is that the best possible expected regret for a worst case adversary is governed not by the VC dimension, but by something else known as the Littlestone dimension. It's not important for this talk that you know what the Littlestone dimension is. Basically, it just says, like, you know, how many iterations can you simulate the example I just showed you with 1D thresholds? That's basically what the Littlestone dimension is. And that turns out to govern the regret you can expect to get with a worst case adversary. Okay. And so here we saw this is plus infinity. This is infinite, even when H is just merely 1D threshold functions. This is already embedded in most hypothesis classes of interest. So this is infinite in any of the hypothesis classes that we care about, which means this is what the picture looks like. Okay, so with an IID adversary average case, we get this bound of VC dimension, governed by the VC dimension, and in the worst case, the Littlestone dimension, this is often small, this is often infinite, which checks all of the boxes for there being interesting sort of theorems to prove in between. Okay? And again, as we said earlier, whenever you have this big gap, it's now also obvious what's the theorem you want to prove. You want to prove that even under just sort of a relatively mild relaxation of the worst case adversary, that's already enough to get positive results almost as good as what you got in the average case. Okay, so the theorem we're going to be striving for is filling in these question marks with something which is not too much higher than this, and therefore much, much, much lower than that. Okay. Great. So, what is going to be the specific model, specific hybrid between worst and average case analysis? Okay. So we're going to be looking at adversaries that are adaptive, are trying to be as sort of nefarious as they can, but we're going to restrict them to choosing not single points, but rather sigma smooth distributions. Okay. By which I mean distributions whose density function is pointwise, no bigger than 1 over sigma times the uniform distribution. Okay, so sigma here is going to be a parameter. Okay, and I encourage you to think about these sigma smooth distributions. I mean, you know, all the results are more general, but really just imagine that the adversary picks sort of a little region of the space capital X, and then picks a point uniformly from that small region. And sigma is controlling how big that region needs to be. Okay, so you've got X, let's say it just has overall measure 1, and then there's going to be some region of measure sigma, and the adversary is going to be picking uniformly from sigma. Okay, that's an example of a sigma smooth distribution, but arbitrary sigma smooth distributions are just convex combinations of these, so it's generally sufficient just to think about that special case. Okay. Yeah.
You mentioned uniform distribution on X, so you just assume that X has some underlying measure.
Yeah, I think of X as like a bounded, so compact subset of Euclidean space or something like that. Yeah,
It's not a general space.
Not for my purposes. Yeah, not for my purposes. Yeah, no, I need there to be a uniform distribution. Yeah, or at least for my talk, I need there to be a uniform distribution. So the adversary, right? The worst case, I kind of like to think of the adversary as like sort of trying to throw darts at this dartboard, right? So I'm trying to sort of, hit little bullseyes that would be really bad for my algorithm. And so for the worst case adversary, you get sort of infinite precision. The adversary can literally just, hit whatever bullseye you want. And then every time the adversary drinks a beer, sigma gets a little bit bigger. Okay? Its accuracy gets a little less good. All right. So it has a couple beers, sigma's positive, and now all of a sudden, all the adversary can guarantee is that it's going to be somewhere in here. Okay, that's the picture I want you to have in mind. Okay. All right. This is what we mean by requiring sufficient anti-concentration. Okay. And going back to the economist sort of asking me about sort of interpretability, right? So how do I think of this model? I don't think of this model as like, a literal model of like reality. That's kind of not the point, right? The point is that on the one hand, we've got our IID models where we love the results and don't believe the model. We've got our worst case sort of model where we have no issues with the lack of assumptions, but we have issues with the conclusion of our theorems that they kind of are not very good. And in particular, we want to allow like correlations, right, between sort of different inputs potentially, but we don't want to commit to any particular form of correlation, right? So we want to just make minimal assumptions subject to there being very strong positive results. Okay, and this turns out to be a sweet spot of exactly that form. Okay. All right, so here's the way sequential prediction is going to work now. Okay, similar to before. But now again, the adversary is not going to choose XT. It's going to be collaboration between the adversary and nature. So the adversary gets to choose a sigma smooth distribution DT, so like a region of X. Nature will then sample XT from that distribution, okay? And the algorithm is again going to be asked to predict the label for XT, and then after that prediction, the adversary gets to choose whatever label it wants as the in hindsight correct label for that input, okay? And again, and this again is where one of the technical challenges come from, is that the adversary is adaptive. Okay, so the adversary gets to see everything that happened in the previous time steps, including, for example, the realization of the instance from the distribution that it picked in the past. And if you think about it, this allows these distributions, these XTs, these are now, forget about uniform, they're also not independent, right? So for example, as an adversary, maybe time step one, you throw a dart, right, and it hits somewhere in this region, like maybe it hits up there in the northeast corner. And then maybe given that the dart hit the northeast corner, maybe you pick your next region centered around that. But if that dart had been in the southwest corner, you would have picked your next region centered around that. Okay. So it does allow correlations, which is both one of the reasons we like it, because we would like to allow correlations in the inputs without having some kind of overly specific model of it. But it's also going to be one of the reasons that sort of, at least to us for a long time, seem to break traditional techniques for proving these kinds of results.
Yeah, in some sense, you may have answered the question already, but that did strike me as a kind of slightly strong choice as a modeling choice, because you're giving your adversary kind of all this power, as opposed to kind of allowing some dependence, like just a Markov dependence, as opposed to playing through the entire history. So
you're saying it's a relatively powerful adversary.
It seems like an all-powerful adversary. It seems.
Yeah, the only thing you've got going for you is there's going to be a little bit of anti-concentration in these distributions. That's all you've got.
Right.
So, in general, other than other,
why did you do that instead of Markov? Is somehow the thing that I couldn't figure out.
Good. Yeah. I mean, this just to keep the running theme of kind of computer science and economist differences, right? So sometimes the way I summarize the difference between like computer science theorists and econ theorists. Right, so obviously the theorem we love has like no assumptions in the super powerful conclusion, and that theorem's always false. So you got to compromise. And I sort of, my cartoon of CS theorists is we just refuse to make any additional assumptions, and the conclusion just is whatever it is, right? If it's hard to approximate with an n to the 1 minus epsilon, it's hard to approximate with an n to the 1 minus epsilon, and that's the answer. Economists are unwilling to compromise on the conclusion, right? So they really want something to be optimal, and they will make any number of kitchen sink assumptions on the hypothesis side to get that conclusion. Again, obviously that's an overgeneralization, but this does explain some of the differences in the type of work you see. So in my work here, I'm kind of unabashedly taking the theoretical computer science approach. So I'm starting from zero assumptions, and I'm asking, can I prove anything interesting? It didn't work. My lower bounds are too strong. What about like the next most minimal assumption I can possibly think of, which is where we are now? Can I prove positive results? As we'll see, the answer is yes. And now I can stop. And so I wrote a paper about it. So that's kind of the process that a lot of us theoretical computer scientists go through when we're coming up with this. So good. All right, so the adversary is adaptive, and so in particular, the choice of later distributions can depend on the realizations of earlier points, which introduces correlation between the different XTs. Okay. So here's the main result of the paper. This is joint work with Nika Hagtalab, who's an assistant professor at UC Berkeley. Abhishek Shetty was her student, is a postdoc at MIT now, and is about to start a tenure track at Georgia Tech. So good news. So with sigma smooth adversaries, there is an algorithm that no matter what the hypothesis class, no matter what strategy the sigma smooth adversary takes, gets expected to be governed by the VC dimension. Okay. So this is the same thing we had before for IID adversaries, except there's this extra log 1 over delta. Okay. Again, the tilde is suppressing log factors. So I've suppressed a log factor like in T here, for example, and some log factors. I've deliberately not suppressed the log dependence on 1 over sigma. That's something I actually really want to highlight. Okay. And again, just to remind you sort of where this fits, right? So we had the worst case, Littlestone dimension, often infinite. Average case, VC dimension, we're often happy with this. So what we have is exactly the same as with an IID adversary, just with this additional root log 1 over sigma dependence. Okay. Now notice, as sigma goes to 0, right, we're getting back to the worst case adversary. So we definitely knew there was going to be some dependence on 1 over sigma here. And actually, it was sort of a surprise to us, very pleasant surprise, that the dependence is as benign as it is. So you can actually take sigma to be exponentially small and still get meaningful learning results. And that's actually different than all of the running time analyses I talked about before. So like that Fox paper I mentioned that's coming out in a month, that paper is sort of, big result is it pins down the necessary dependence on 1 over sigma, the running time of the simplex method, and that's root 1 over sigma. Here we're getting root log 1 over sigma. I mean, that's running time. This is regret. There's no reason to think it's apples to apples. But still, we were conditioned to more expect polynomial dependence on 1 over sigma. We got log dependence. We were very, very happy about that. Okay. And also, so here I just said O tilde. Here it's theta tilde. And indeed, in the paper, we show that you really do need at least this dependence on 1 over sigma. Okay, so root log 1 over sigma dependence is tight. Okay. And this also answers the main open question of a old paper of Rockland, Schroeder, and Tawari. Right? So questions before I tell you a little bit about the techniques that go into this. Don't have that much time, I guess, but yeah.
The algorithm come before or after the model?
Good question. I would say the algorithm is one. The algorithm that we use for this, in effect, is the same one you might use for the average case. So you should think of this as just our contribution is in the analysis and showing that this algorithmic approach works under much weaker assumptions than you might have expected.
I have a follow-up to an earlier question. Like the game you're playing with X and H doesn't really depend on how X sits inside Rn, right? But your sigma does. Like you could imagine moving X around in Rn and H with it, but then the sigma changes. I'm just wondering if there's a way to.
Well, why does the sigma change? Sigma is just like how much are you allowed to scale up the density function relative to the uniform distribution?
Yeah, maybe the notion of uniform distribution that can sort of stretch X.
Yeah.
So maybe I'm misunderstanding the thing. I'm just wondering if there's a way of saying sigma that doesn't.
Yeah, no, I'm not. I mean, you could imagine trying to generalize this further to other measures. I mean, for this talk, and for the most part in my mind, I'm literally just thinking about like Lebesgue measure, complex subsets of Rn, which covers, which is typically what you're interested in machine learning applications. That said, I mean, a lot of that, like the smoothness notion, it doesn't have to be relative to the uniform distribution. It could be relative to some other base measure. There are extensions of that form one could do, but that I'm not going to emphasize those today. Yeah. Okay. So let me just. All right. Well, I'll say a bit about the proof. Okay. So if you haven't seen this stuff before, if you don't have any background in learning theory, the first question is like, okay, VC dimension, sort of by definition, it's an obstruction to fast learning. So it's very easy to see like why you can't learn if the VC dimension is high. But if all I tell you about a hypothesis class is the VC dimension is small, like, okay, I guess every big set like can't be shattered. Like, what do I do with that? So you got to kind of get going. Like, how does the VC dimension hypothesis like do things for you? Okay. And so the root of all of it is there's this sort of just very cool fact. And it's not obvious. I think it's kind of surprising. The proof is one of those like short, slick inductions. You're like, wow, that's like a Hall of Fame induction proof right there. So what I want you to think about, so you got your hypothesis class, you've got your domain X. I want you to think about finite subsets of the domain of bigger and bigger sizes. And want to look at how many Boolean functions, distinct Boolean functions, are induced on that finite subset by the hypothesis class. So up until the VC dimension, up until D, it's growing exponentially because you're shattering all those sets up to D. So you're getting all 2 to the D Boolean functions. But what's amazing is that as soon as you get past the VC dimension, as soon as you get past that threshold, actually the number of distinct Boolean functions you see grows only polynomially with the size of that set. Okay? Not obvious, not hard to prove, very powerful. That kind of, if you think about like the best possible combination of properties for a result. Okay, and so one thing you can do with this is you can show that bounded VC dimension hypotheses in some sense behave a lot like Euclidean space when it comes to packings and coverings. Okay, so you can have so H in general is going to be infinite, right? Half spaces, polynomial thresholds, whatever. But there's a good finite proxy for it with respect to the uniform distribution. Okay, so given a generally infinite capital H of bounded VC dimension, you can pick a finite subset H prime that is close to that can proxy for any hypothesis in the set capital H. So precisely for any H in capital H, there exists H prime in big H prime, so that the disagreement region between H and its proxy H prime is less than epsilon with respect to the uniform measure. Okay. So that's what I mean by an epsilon cover. Epsilon here is a parameter we're going to be playing with. And the size is going to be exponential in the VC dimension with a base of not 1 over epsilon, but 40 over epsilon or something like that. Okay. So that's the first good thing about bounded VC dimension. It means you can take an infinite class and proxy it with this finite class. And then what that sort of dovetails into is we've known for a long time that the finite cases in some sense, maybe easy is the wrong word, but well solved. So this is something I teach beginning graduate students in my classes, which is if you only have a finite number of hypotheses, you can use these very elegant, very simple algorithms. They have names like hedge, multiplicative weights, et cetera, that get good regret bounds. Okay. And so the approach here is just that, okay, you get a new data point. And what you're going to do, you have this finite set of hypotheses now by assumption. You pick a hypothesis at random from an appropriate distribution, and then you use that hypothesis to predict the current point. Okay. Now, you're not going to pick a hypothesis uniformly at random. Hypotheses that you've observed to do better in the past, you're going to pick with higher probability. So with each hypothesis, you maintain a weight, and the weights evolve over time. So for example, maybe the weight gets multiplied by 1 plus eta, goes up if it was correct on a data point, or it drops by 1 minus eta if it was incorrect on a data point. And at any given time step, you're going to choose a hypothesis with probability proportional to these rates. And if you tune all the formulas and parameters appropriately, you get what are optimal regret bounds. Okay, so specifically, algorithms of this form, and again, this is with a finite set of hypotheses, capital H, it's for that special case. The regret scales as log of the hypothesis size times t square root. Okay. This is also the maximum VC dimension of the finite set. So it's sort of consistent with those results that we saw. Okay. So VC dimension allows you to have a finite size proxy, and finite sets we kind of know what to do with using these Vosper algorithms from the 80s, if not before. Okay. So the algorithm at this point is going to be, I think, the obvious one. You take your hypothesis class, you replace it with an epsilon cover H prime. Okay, again, of size roughly 1 over epsilon to the VC dimension. What is epsilon? We'll figure that out. We'll choose that later. And then we just run an off-the-shelf, your favorite algorithm for the finite case on H prime. Okay. All right. So, but on the other hand, like we know with a worst case adversary, this is not going to work. Right? We know with a worst case adversary, like with those 1D threshold functions, we might be making mistakes forever. Okay. So how is that going to show up in the analysis? Easy to show that you can bound the regret of this algorithm by, on the one hand, what you inherit already from the finite case. So that's going to be square root of log of h prime, finite proxy, times t, plus the approximation error. Okay. I'm a little sloppy with the notation here. Really, this is the maximum over all hypotheses h in the original class and the corresponding epsilon closed proxy h prime. Okay. So this is an h and an h prime where the measure in the disagreement region is less than epsilon. Okay. And so what I'm saying here is that in addition to what you get from the finite case, there's an additional approximation error depending on how many of the data points in hindsight wind up in one of those sort of disagreement regions of measure less than epsilon. Okay. And now you see why, with the worst case adversary, you're going to be toast. Right? The worst case adversary can just pick its favorite HH prime pair and literally just pick all the HIs in that disagreement region. And this is a meaningless bound. On the other hand, if these are drawn from, distributions with some amount of anti-concentration, say where, I should have said this, you definitely think of like epsilon as a lot smaller than sigma. Okay. So the adversary can try to, throw its darts and get the xi's in this small region epsilon, but it's had a few beers and it's going to be in this space of sigma instead. So you can imagine it might be hard for that kind of adversary to get these numbers to be high, but you still have to prove it. Okay? All right, so I really have to wrap up. Okay, so the second way in which finite VC dimension helps is just as far as concentration of measure. Okay? So basically, for any given pair HH prime of nearby hypotheses, you can use Bernstein's inequality to get sort of a deviation like this. We're using here the fact that the events are that the disagreement regions are low measure, and we're using Bernstein's inequality to get this epsilon underneath the square root. It's actually really important for us to get that log 1 over sigma dependence as opposed to a 1 over sigma dependence. And then, again, the nice properties of bounded VC dimension help you take a union bound over much fewer things than you might expect, which is why on top of the root epsilon t you get for a single hypothesis pair, union bound over everything, you only pay an additional factor of the VC dimension. Okay? That's some of those magical properties of bounded VC sets. Okay? All right. Now, I should have said, so you get this concentration of measure in the case where you have a benign adversary. Okay? In the case where the xi's are generated IID uniform. And the whole point of what we're trying to prove is that the xi's are generated by an adaptive smooth adversary. So forget about not being uniform. What sort of scared us even more is they're not even independent. And we didn't really buy it. We set up our model so we have very little understanding of the correlations between the different x's. Okay. And I have to tell you, we were kind of stuck. I'm sure you've all had this experience where, you work on a problem forever and you're like throwing the kitchen sink at it. And just, it could be years later, you get unblocked by like what in hindsight is like a simple trick. And like, that if someone just whispered in your ear, there's a simple trick to fix this. If you had that piece of advice, you would have found it very quickly, right? It had to occur to you that there might be an easy way out. And that's actually kind of what happened to us here. I can't get into the details, but so we spent a long time trying to extend all of the machinery that's been developed for independent distributions to handle the type of correlated distributions that come up with a sigma smooth adversary. But as it turns out, you can reduce the case of a sigma smooth adversary to the case of an IID adversary, modulo a sort of negligible failure probability you can handle separately. So you can do this using a coupling, right? So again, rather than just sample xi, we're going to sample a bunch of auxiliary random variables, sort of wi1 through wik. A coupling, that's just a joint distribution on the x's and the w's. It's going to be the case that the x's are going to be a bona fide sample from the adversary's distributions, as we've promised to do. Yet, these w's are going to be uniform IID samples, and with overwhelming probability, the xi will actually be a member of the set of uniform random variables that we generate. Okay? So on one hand, we generate a point like from this sigma region. On the other hand, we generate k points uniformly at random, and we couple those two processes in a way that almost all of the time, one of the k uniform random variables that we sample actually lies in sigma. And we can use that as the adversary's data point. And so what this morally shows is that, sigma smooth distributions can be in some sense dominated by IID uniform samples at a longer time scale, okay, with time blown up by something that scales with, in particular, 1 over sigma, okay? So with this coupling, you can plug these into the earlier concentration and measure bounds that I told you about. You can set K. K is sort of the blow up, how many uniform samples you need to dominate a sigma smooth sample. If you set that appropriately, in fact, all of the error from the approximation error kind of goes away, and the regret bound is dominated by what you inherit from the finite case, which again, remember, is the VC dimension times log 1 over epsilon. So epsilon is ballpark 1 over sigma. So that's exactly where our square root log 1 over sigma dependence is coming from. Okay. And so again, just to remind you of the result, this is what we just proved. And again, the dependence on sigma is indeed necessary there. And basically we get just as good as the average case, except with this degradation in sigma as it goes to 0, and in particular, way, 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 way better than the worst case, okay, which is kind of the happy event you want in smooth analysis. Talk to me later if you want to hear about applications in online discrepancy minimization. I know I'm out of time, so let me just leave up the final slide and stop there. Thanks.
Questions?
What is the dependency in the underlying dimension n? X leaves
On n, so that's going to show up here. It's going to depend on, so in general, right, so like for half spaces, this is going to be, n or n plus 1. If you have sort of degree d polynomial threshold functions, this is going to be like n to the d, where d is the, where d is the degree and then n is the dimension of the Euclidean space you're working in.
So the theta doesn't depend on the underlying dimension.
Yeah, correct. So this one, yeah. So in fact, this does not suppress. This is suppressing a log t factor and log factors. So the dependence on the VC dimension is truly linear in the VC dimension. This is not suppressing any log factors in that. Yeah. Yeah.
Okay. So this trick that you mentioned at the end, this coupling between the smooth distribution and the IID, I mean, is this the main thing that's used in this kind of analysis, or there are many different ones? So for example, in the semi-random model for CSPs, there are these new spectral methods that seem very different.
Yeah, I mean, it took us a long time to come, what was there to say? I mean, like, I think all of us were trained in certain cases where you're used to seeing couplings be a key tool, and this was not one of them. And so that's why it took us we had to iterate through a lot of things that didn't work before we came on this. So the good news is, I think this is actually like a new, that's sort of the point of this online discrepancy minimization. Once we came up with this, we said, this actually seems like it's pretty simple. It's fairly black box, like fairly modular. There should be other places we should be able to use it. And so, for example, in online discrepancy minimization is one place where, again, we kind of plug in that same coupling to get a result that wasn't known before. I'm guessing there are others. So in part, I want to publicize this trick because I think other people might find it useful in their own work. But we were surprised to see it in this context. But the good news is, maybe there's a lot of other things we can do with it then. Yeah.
More questions? Okay.
All right. Thanks again.
Thanks again.